So the next talk is by Kelley et al. On the assessment of subsidence risk associated with aquifer storage and recovery in the coastal lowlands aquifer system, Houston, Texas, USA. So please, the floor is yours.
Great, thank you. So good morning, everybody. My name is Ashley Gruder, and I work for the Harris-Galveston Subsidence District. And I'm really excited to give this presentation that was done with our lead author, Van Kelley, Mike Turco, Neil Deeds, myself, and Chris Canonico. So this is just a typical, what happens with every science project, an introduction, objective, methodology, results, and conclusions. So I'll start with a background on the hydrogeology of our region. And then I did include just a map of the United States, and then that tiny, tiny little outline, which is, whoa, this clicker, there we go, which is right here, are the two counties in Texas that we regulate, Harris and Galveston counties. So the Gulf Coast Aquifer, where the coastal lowlands is what typically we call it, is the Gulf Coast Aquifer in our region, is composed of three primary water-bearing units. The Chico Evangeline, which is undifferentiated, it's hydraulically connected, and then separated by the Burkeville confining unit, and then we have the Jasper Aquifer, which is shown in green. Primarily for permittees in Harris and Galveston counties, they take their groundwater from the Chico and Evangeline, so those are the ones that I'm going to be focusing on. And with depths ranging from, I know this is in feet, but around 90 meters to about over 1,500 meters in our region. So I won't cover too much of the mechanisms of subsidence because, towards the end of this conference, I feel like y'all pretty much know that subsidence can happen due to aquifer compaction. So I'll skip over this mechanism, but isn't it a lovely little schematic that we have to help show for the general public why subsidence is occurring in our region? So I'm really excited to share this, as Michelle showed earlier for the case of California, where they had that famous poll in the different subsidence and elevations. We now have one for the Houston region. And you can see here historical subsidence that was measured in our region. John Ellis with the USGS is proudly holding that surveying rod. And then you can see the different time intervals where they've actually collected data on those units. So that concrete base here at the bottom is this benchmark, PTS 185. And throughout time, over a century, we've been collecting benchmark data on it. So elevation data of where that's been sitting in time. And we can see from 1915 at the top to around 1976, there has been about 9 feet or about 3 meters of subsidence. So this is specifically important for our region, and I want to showcase from this poll, we have these dates. They're also shown more graphically on the map for all of us data nerds who like to see it represented graphically. So you can see those actual red points correlate to those times on the poll, and we can see a decline. That tan line underneath is the groundwater levels that has been collected from a nearby monitoring well. And we can see that there's a relationship in that same decreasing trend from the land surface elevation and the groundwater levels. But then something happens right around that 1976, and you can see it both graphically at this inflection point with the groundwater starting to rise, and then the land has really stopped and leveled out. And we can see that on the poll as well. From 1976 to 2021, there's basically no subsidence. So what do you think happened in this time period to make this drastic change? Well, it's a rhetorical question, so I'm not expecting any of you to raise your hands. But if you were attending talks earlier by my colleague, Mike Turco, he actually introduced this Harris-Galveston Subsidence District. And this is the key of when we were formed and established with the mission to regulate subsidence in our region. We do this through the regulation of groundwater withdrawal, and I won't touch upon all of these points and specifically what we do because Mike covered that earlier, but I do want to showcase the formation of the district and why it's so important for us. So another part, before I dive into all the modeling methodologies and results and what we did, I think it's really important to understand why we did this study in the first place. Like, it's great to have all this data and talk about all this work, but why is it important and what are we going to do with it? So I'll start with the map on the left. This is showing subsidence that has been measured at benchmarks like the one I previously shown from 1906 to 1978. And this mainly represents the period of time before the district was founded. And we can see, I've also shown within those contour lines, which are in green, those contour lines are different regulatory areas. So you'll see the major cones of subsidence are happening along the Houston Ship Channel, which, oh, this is much better like this, which is right in here. Hopefully you can see that on that, yes. And then here in Galveston County in the blue, with over 9 feet of subsidence in that Houston Ship Channel, and then over 6 feet in the Texas City area. This basically was how the district first started regulating in these areas that were subsiding the quickest. So this regulatory area 1, shown in blue polygon, is only allowed to use 10% of groundwater from their total water demand. So permittees, people who have wells in this area, they say we need this much water a year. Well, we as the subsidence district say, based on your location, you can only use 10% of groundwater because of all the subsidence that has happened. But then note, they've converted to alternative source waters. The main one for us is surface water, shown with Lake Houston, which is right here in regulatory area 3, which gets a lot of water also from the Trinity River further to the east. This area and regulatory area 2, which is shown in that yellow polygon, converted back in 1990 and 1995. So what this means, there's only 10%, and then regulatory area 2 has 20% of groundwater for their total water demand. And we can really see the impact of this regulation on that map that's from 2000 to 2020 here, where we have the same regulatory areas doing the same benchmark analysis, so getting that same survey data on those same benchmarks, over 170 throughout our region. And we can see there's no subsidence in these areas that have fully converted. So this really is a testament to the success of our management of the regulations with groundwater withdrawal in our areas. And this is specifically important for this project because we want to ensure and encourage permittees to have alternative source waters, but we don't want any alternative source waters to diminish the success that we've been able to achieve in our area. So aquifer storage and recovery, just a quick introduction, has been considered by a lot of industrial and municipal water suppliers in the district. It's a way to use the aquifer to store that excess water during times of plenty and then be able to use it when in times of need. This diagram shows the basic concept, which includes an injection well and then recharging that aquifer, usually with treated surface water that's then stored and intermingles with the native groundwater in this little buffer zone that we see here right in the middle. And if we take the ends from this little bubble where we have that stored water that's being injected to the buffer zone, this represents that total or target storage volume. So, and just like this is a surface reservoir, a properly designed ASR project will define a yield or a storage volume over a specified time horizon. So let's review the details for this study. The first objective that we had was to review literature on ASR in subsidence-prone environments. So based on the time that I have for this talk, I'm not going to get into these details, but just know that we looked at 3 valleys in California, Las Vegas, and also Shanghai. And then next, we wanted to estimate the subsidence neutral yield of a typical ASR project as researched from those examples in the first step. Now, for those of you scratching your head thinking, what is a subsidence neutral yield? Well, let me explain a little further. Subsidence neutral yield is defined as the percentage of recharge storage volume recoverable from an AR well without causing additional subsidence. Or in other words, it's recovered water from an ASR project that will not cause additional subsidence. Remember, it's important, due to the success that we've had in our region, we don't want to have projects that will contribute to subsidence. We want to be able to minimize no additional subsidence. So then we analyzed potential water quality impacts on native groundwater. And again, due to the timing, I'm not going to go into the details of this, but I'll mention that a lot of geochemical analyses were performed on treated water samples to determine geochemical capability, or compatibility, excuse me. Potential problems identified were calcite precipitation, which can cause a plugging problem in the wells, and iron, specifically pyrite and siderite oxidation and dissolution that might mobilize arsenic and increase the total dissolved solids of the recovered water. And finally, we wanted to have a foundational knowledge base to evaluate ASR projects, including regulatory considerations for our region. So now let's explore how we achieved those objectives. So we began with 2 hypothetical cases in Regulatory Area 1, as they are required to use the least amount of groundwater in our district. And they are also the furthest away from these alternative supplies. As we can see, the Lake Houston is now completely off the map. This is Regulatory Area 1, and they also get water from the Brazos, which is also further to the west off the screen. The first one that was designed was for a drought of record, herein DOR, for industrial users. In this case, we analyzed Gulf Coast Water Authority's water supply contracts to determine industrial customers' water volume and the amount of water that was delivered to such customers during the major drought in 2011. And from this, we were able to determine percentages across a 5-year period. So for us, this drought in this study is considered over a 5-year time interval. The other scenario that we looked at was peak summer demand for municipal users. So we used peak potable water demand and projections from a large regional water supply project to estimate peak conditions, which are about 1.4 times an average demand. We selected 3 potential locations as shown on the map with this blue triangle, this kind of black hexagon, and then that green square at the bottom right in Galveston Island. We also, in addition to looking at them, used the geophysical logs to obtain values for parameters that were going to be used in modeling, such as lithological composition and hydraulic properties. And this geophysical log here shown is for the base case. So this log right here is for this black dot. And I couldn't resist showing a geophysical log, so in case, for those of you who aren't geologists and don't know what all these squiggle means, it's nicely color-coded. So you can see we have beautiful sands here in the Chico Aquifer, and the blue is that fresh water, that good quality water that you would actually want to be using for your supply. So now we considered recharge and recovery cycles as part of our conceptual design for this ASR project. For the DOR case, we were assuming a 5 million gallons per day recovery over that 5-year time interval. And this graph shows the cumulative water stored in millions of gallons, sorry for the different metrics that we use here in the States, shown as that red line, or it kind of looks almost orange on this screen here. And then the recovery or the recharge rate in millions of gallons per day, which is in this blue line here. The total storage volume was roughly about 9 billion gallons, and it takes a few times of recharge at that 5 million gallons per day to achieve this volume. But this is what this line is showing right here. Nope, sorry, this is that one right up there. And after that value is established, the recovery cycle begins around year 5, following a specified schedule with the goal of recharge and recovery at that 5 million gallons per day. So what I'll draw your attention to is at the end right here. So notice that this is not zero. There's still remaining water in this ASR well. This represents the buffer zone volume. As I showed previously, we have the bubble in the middle, and then we have the buffer, and then we have the native groundwater. So we don't want to take all the water out of there, because in this buffer zone with the intermingling, you'd have to be seriously treated if you wanted to use it. So it's best to just leave it in place. And the next example we have is that summer peaking, our case 2, which had a conservative total storage volume of 1.3 billion gallons. And the same kind of applies. This is that storage volume, which is in that orange. And then the recharge or production, producing or pumping back in, is shown in the blue. The recharge was almost 6 million gallons per day, and the production was about 7. And even though the volumes between the drought of record, the DOR, and the summer peaking case were very different, the rates, in fact, were very similar.
Ashley, 2 more minutes.
Okay, so that's a review of the input parameters. I'm not going to go into all the details of this table, but basically we were taking that geophysical log to use as parameters for our cell. All of that good stuff for all of you geomodelers who like all that is the details are there, but I won't get into it too much due to time. So now into some of the results that we have. For the drought of record, we see that once recovery occurs, the heads, which are shown there in the blue, decrease quickly in response to pumping, which is as expected. And the corresponding compaction, it changes to head is plotted with the maximum in the red and the minimum in the black and the dashed lines. And over the course of the operational period, the maximum compaction is about 6 centimeters that we see here. And each time a recovery cycle occurs, some compaction is also experienced. And then for the summer peaking case, the head increases to about 27.5 meters during the recharge, and then the drawdown of about 35 meters during that recovery. And the first cycle experiences the greatest change in compaction. Again, at the end of this, we have about 5.5 centimeters of compaction. So I also want to show really quickly the recharge influence on compaction from ASR. This compares the compaction through time for both scenarios. And it's also showing what happens if you recharge that ASR well in addition to pumping. So due to time, I'm only going to focus on this summer peaking because we see this wide range here of if you actually do recharge it, which is shown in the blue, or if you don't. And this difference is about 30%. So it's showing it's very important if you want to minimize compaction in this area with an ASR well to also be sure that you're recharging it as well. Other considerations that we looked at, but I don't have time to show all those graphs, were project location. Remember, I showed 3, and I was only showing the base case in this scenario. Also, well spacing, how far out you are doing it, where you're going to put your screens, stacked or not stacked, things like that. Recovery durations as well. And then which layers, there were 11 total, finding the best vertical conductivity. And it is important when you're designing this to take these in consideration because some of these, if not properly designed, can have as much as 50% more compaction. So for the non-modelers who are interested in maybe some regulatory, really quick, we also considered the regulatory aspect of this. We at the district only regulate groundwater withdrawal. If a permittee would like to use ASR, they would actually have to permit that through a separate entity, through the TCEQ. And this is kind of how that process would go with first registration, doing a drilling test, getting your data to be actually feed the model. You'd submit a permit with the TCEQ. That is a lengthy process and time consuming because that has public comment as well. And then do all this modeling, some of that fun stuff I was showing earlier, and then submit a management plan to us. And then we at HGSD would then permit with annual monitoring and reporting. So the main conclusions, really quick to wrap up. Recharge was really important as we saw 30% less compaction. Also reducing the duration of drawdown results in less compaction as well. And these are some high-level design factors to really consider for your planning to mitigate some compaction. This QR code also will take you to that full report. It's quite lengthy, but it's got a lot of good stuff. So if any of this piqued your interest, be sure to use that, and that will take you directly to the site from our website. And hopefully I didn't go too far over, but thank you for your time.
Yes, thank you very much for this interesting presentation. We have time for one question.
Thanks for the presentation. Just one little question. You are not expecting rebound from the aquifer because I have seen the subsidence stops, but doesn't exist. It seems that it's not an elastic response to the stop of the pumping.
Yeah, so great question on rebound. The results that I was showing was in a model layer 4, and you can tweak how you want your delay beds and where you want some of that. So we didn't really see or analyze that. It was more a confined setting where we didn't have that. Hopefully that answers, your question, sure.
Great. Thank you.
Thank you.